Polarization. Unpolarized light passing through a polarizing filter will become polarized. If it is a linear polarizing filter, then we will have plain polarized light that passes through it. If we have two polarizing filters, one after the other, then that plane of polarization can be rotated around by the second filter. So what do we mean by polarization? Well, here I've got a very simple sketch of an electric field and a magnetic field for an electromagnetic wave. The electric field varies sinusoidally over time as the wave is transmitted through space. The magnetic field also varies in the same way. And it is the electric field component that we are interested in. The electric field component, which here is shown vertically, is the field that we polarize. The magnetic field component will always be right angles to the electric field component, but we're not as interested in that at the moment. So, here I have a diagram that shows a plane of polarization before the filter being vertical. That's represented by this red arrow here. And this red arrow shows the variation of electric field strength if we view the electromagnetic wave we saw earlier from the end of the z-axis. That is to say, from this position here, we can see the vertical variation of electric field strength as the wave passes towards us. Now, if we place a polarizing filter at some angle, theta, then that polarizing filter will select only one plane of polarization, which is parallel to the direction of the polarizing filter. And you can see from trigonometry that if the angle of the polarizing filter to the vertical is theta, and we have vertically plane polarized light before the filter, then A, the amplitude of the electric field variation multiplied by cosine theta becomes this new amplitude of electric field variation. It's cosine because the original plane of polarization is the hypotenuse. Polarizing filters will always reduce the amplitude of the electric field variation. We'll also need to remember our equation for intensity and amplitude, which was covered in section D1 in your Isaac physics book. If our amplitude halves, then our intensity will in fact go down by a quarter, because our intensity varies as the square of the amplitude. So let us have a look at a question. Here we have two polarizing filters, one at 60 degrees to the vertical, one at 120 degrees to the vertical. And we're going to illuminate them with vertically plane polarized light, which has 100 volts per meter amplitude and 16 watts per square meter intensity. And we want to know what the light looks like when it comes out. That is to say, what the amplitude of that light is and what the intensity is. Well, let's start with amplitude. As this electromagnetic wave passes through the first filter, the amplitude is reduced. It is reduced by a factor of cosine theta. So it goes from being 100 volts per meter to becoming, our new amplitude, becoming 100 multiplied by cosine of 60. So our new amplitude is 50 volts per meter. If we do that again at the second filter is 120 degrees to the vertical, but that means that it is 60 degrees to the previous filter. And so our new amplitude is going to be our 50 volts per meter here, multiplied by cosine of 60, because there are 60 degrees between the second polarizing filter and the first. And that will give us 25 volts per meter. So what happens to the intensity? Well, the amplitude has gone down by a factor of 4. It is a quarter of what it was before. And so because the intensity varies as the square of the amplitude, if the amplitude is reduced by a factor of 4, then the intensity has been reduced by a factor of 4 squared, which is 16. So our new intensity is 1/16 of 16 watts per square meter. So we can work that out very formally by using I equals K A squared. and you can find that K equals I divided by A squared, which initially is 16 divided by 100 squared. 1.6 times 10 to the negative 3. If we multiply the square of our new amplitude by K, that will give us our new intensity. So our new intensity will be K multiplied by our new amplitude. This is after both polarizing filters, and that's squared. 1.6 times 10 to the negative 3 multiplied by 25 squared, which is 625, and that gives us just 1 watt per square meter. So our final amplitude was 25 volts per meter, and our final intensity was 1 watt per square meter.